cooperation in mathematics between Brazil and France. I was told that for people who are in the back of the room, there's the same talk being shown on the screen in the two rooms adjacent to this. So if you want to not stand up during this conference, you can see what's happening on the side. I'd like to present Etienne Ghys. He's going to give 5 talks, so I'll just spend a few moments talking about Etienne. This is a paper I found on internet, which is really delightful to read. I was told just now by Etienne that it was prepared for his entrance to the Académie des Sciences de Paris, de la France. And it's a talk that shows that Etienne has a great talent and passion for writing and doing mathematics. This text concerns dynamical systems on Romanian manifolds. That's the theme in the text. And dynamical system is a very general notion for Etienne. It can be a vector field on a manifold. It can be a diffeomorphism or a group acting on the manifold, or a pseudogroup that comes from a foliation and the whole norm of the foliation, or more generally can be Brownian motion on a lamination of a Romanian manifold. And all these things are considered in this paper. It's really a delightful paper to read. Let's say 1/3 of the paper is concerned with a special case that's going to be present in the 5 talks he gives. Associated to a Romanian manifold, there's a natural dynamical system that comes from the geodesic flow on the unit tangent bundle. And this is very well studied, and in particular about 1/3 of this paper of Etienne studies this question. For example, when the manifold has negative curvature, then there's great stability properties and ergodicity properties of this geodesic flow. And the idea is to try and understand when does the dynamical system give you information about the geometry of the Romanian manifold, and when does the geometry give you restrictions or information about the dynamical system. And that's what Etienne and people study in this subject. This paper begins by talking about work of Poincaré on vector fields in the plane, and the idea of the Poincaré-Bendixson theorem, which says that the orbits of a vector field in the plane that enter a compact set always have a 0 in the closure, or a compact cycle. And then he passes to talk about Painlevé, who studied 2 complex polynomials in the complex plane, which have no common zeros, and the vector field, the holomorphic vector field defined by 2 polynomials paying q of complex variables z1, z2, and thinking of that as a foliation of the complex projective space. And this study by Painlevé, where the orbits, the non-degenerate orbits now are Riemann surfaces of very interesting topology, inspired Erishman to define foliations, and inspired Rabe and Erishman to create the basics of foliations. And Etienne finishes this section with a very beautiful unsolved problem, which I'd like to mention. It says that if you take, is there a Poincaré-Bendix theorem for holomorphic vector fields of complex projective space? If you take a holomorphic vector field in CP2, does every orbit, so now it's a Riemann surface, have in its closure 0 of the vector field or a compact leaf of the vector field? That's an unsolved problem, which I consider a very beautiful problem.
Which, as far as I know, is due to him.
That's why I'm prejudiced towards the problem. In any case, that's the theme. That shows you, that's the first chapter of this marvelous paper. I really, if you want to enjoy yourself, I suggest you look at this paper on the web and just read the first few chapters. And Etienne is so good at talking about mathematics that it's the last chapters where he talks about his work and his contributions to the theory, which is really magnificent. Okay, well, besides these qualities of Etienne, he also is very active and enthusiastic about divulging mathematics to non-mathematicians. There's a French journal called Le Monde, which the French people here certainly know about, where he's contributed at least 10 papers about various subjects of mathematics that everybody can understand. And these are delightful articles about what's going on in mathematics for non-mathematicians. In 2008, Etienne created a journal. If I can, maybe I have to turn this on. I'd like to change. There we go. Image des mathématiques. So what I'd like to point out about this journal, has a very interesting property. Oh, this is the wrong, I see, it's the wrong direction, that's the problem. Okay. This journal has the property that a pour but de présenter la recherche mathématique, en particulier française, et le métier de mathématicienne à l'extérieur de la communauté scientifique. Tous les articles sont écrits par des mathématiciennes et aucun article n'est écrit pour les mathématiciennes. That's a rather formidable idea to create a journal like that. And it worked. This was created by him in 2008. He was the editor-in-chief for 6 years. And he made a rule that after 6 years, the editor-in-chief had to resign. So he resigned. He respected his rule. And this journal has many, many interesting, delightful articles for non-mathematicians written about contemporary mathematics. Very, very interesting. Etienne also wrote the scenario for a 2-hour video, Dimensions. This goes on for 2 hours. There are 9 chapters to this video. The first chapter is easy. The second chapter is a little less easy. And you get up to 9 where it's sort of more difficult mathematics. So the first chapter talks about Hipparchus, how to describe a position of on the Earth in terms of 2 parameters. So that's common knowledge to us here. The second is a little more interesting. It talks about Escher describing how, if you live on a surface of 2 dimensions, you can see things in 3 dimensions. So this is a conversation of Escher about that. Then I'll skip the next one. I'll go on to the next one. There's a picture there that's the French people here know, at least people of my generation. That's Adrien Douady, who's talking about complex variables. And he's talking about what happens if you take, for example, z squared and you iterate it, and what kind of limit sets do you get. He's talking about complex numbers. So this goes on. It gets more difficult. Perhaps I'll spare you that time. I'll just pass to the last slide here for me. Let me just mention that everything I'm saying up to now, I'm in great admiration for Etienne. The next and last slide I'm going to show you, I'm very jealous of Etienne. Let me tell you why I'm very jealous. Those who are from France and worked in Paris know that when you retire from Paris, there's a line of people outside your office waiting for your office. In the provinces of France, it's not so true, and in Brazil, it's certainly not true. But in Paris, I tell you that when you retire, you're lucky if you manage to find an office somewhere that you share with 7 other 8 people, just a desk. So it's difficult. Etienne's the only mathematician I know who has an office for his whole life in the middle of Paris in a beautiful building, because on January 1st, I'm going to skip some slides here, we go here, there we go. On January 1st, Etienne was elected to be secrétaire perpétuel, that's the word, the important word, perpétuel, des Académies de Sciences, de Mathématiques, Physique, Physique de l'Univers, and Application. That's a magnificent picture, I love it. But a question I could ask Etienne, do you have a sword?
No.
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 I think in the Académie des Sciences et Lettres, you had to have swords with their uniforms.
Well, when I turned 60, my students offered not a sword, but a sabre. How do you say that?
A saber?
Saber. So I have a saber.
Oh, I see. Okay. Well, okay. So that's. Thank you very much. That's the presentation of Etienne.
Thank you, Harold. So Harold told me he would speak 5 minutes. Okay, so thank you, Harold, for being so clever to invite me to this meeting 2 years ago. And 2 years ago, he told me, why don't you give 5 talks? And I said, why not? And now 2 years have passed. I have to give 5 talks. So for me, it's really a great pleasure to be here to celebrate this collaboration between France and Brazil. It seems to be that it was yesterday that I arrived in IMPA. It was 40 years ago. So thank you, IMPA. Thank you, Brazil. Brazil is not in a good shape today. I think this collaboration between France and Brazil will be very constructive and will be forever something very useful. So let me tell you, I have to give 5 talks. Most of you are not geometers. Look, let me tell you, not so long ago, let's say 100 years ago, in the French Academy of Sciences, there was a section called geometry and a section called physics, but there was no section called mathematics. So a long time ago, geometry and mathematics were just synonymous. So I decided that it's much better for me to give you talks which are totally independent. So if you don't come tomorrow, you can go after tomorrow, and there will be completely disjoint. And the other point I decided that I do not want to speak for geometers. So I'll try to do my best to be as elementary as possible and to provide some introduction to old mathematics. Let me mention a quotation by Arnold. Arnold wrote the following: "It is much easier to obtain a new result in an unexplored domain. Hence, most researchers carefully avoid any thinking on the old classical problems. It is useful to compile from time to time the lists of sleeping problems in unfashionable domains, just to know the problems are still open." And finally, he said, he gives his definition of mathematics. Mathematics is the name for those domains in theoretical physics that are temporarily unfashionable. So my purpose in these talks will be to present 5 old theorems, old papers in geometry that I consider very fundamental, very innovative, and I hope these 5 talks will provide 5 beautiful sleeping problems. And again, I try to be as elementary as possible. So today, as you guessed, I want to discuss Monge, Gaspard Monge. I like Gaspard Monge very much for many reasons, mathematically, but also as a human being. He, as you will see, was very much involved in the French Revolution. He was not only a mathematician, but he was active in political and social life in France at the time. So let me say, first of all, a few words about Gaspard Monge. The topic of this talk will be one paper by Monge called Mémoire sur la théorie des déblais et des remblais par Monsieur Monge. I will explain that later. Well, this gives me the opportunity that I am so sorry in a French-Brazilian meeting to have to speak such a language as English. So most of my slides will be in French. I will try some English on it, but too bad, too bad. Okay, a few words about Monge. Monge is above all a geometer. He's the founder of what's called descriptive geometry, which was a fundamental part of the French curriculum in mathematics until 1950. Basically, it tells you how to draw pictures that can be useful for engineers, how to draw geometrical pictures that can be used by engineers. Applications have always been in the heart of the work of Monge. Then he was also an analyst, one of the founders of partial differential equations, at least in their geometrical part. Maybe some of you know the Monge cone for PDE, he one of the very first to try to understand the nature of partial differential equations. And at the end of my talk, you will understand the Monge-Ampere equation, which has been invented by him. He was an applied mathematician. When the French Revolution began, and when all the countries around France were our enemies, our country was in danger, and he decided to stop doing mathematics suddenly and to work for cannons, how to build cannons. He created a school where students would come and would learn how to make cannon, and he wrote a book on the art of making cannons. So that tells you how diverse it was. But the most important for him was teaching. Darboux, after his death, wrote a biography of Monge, and he said that Monge not only created new theorems, but he created new mathematicians. He spent all his life working on teaching, in particular in the École Polytechnique, in the École Normale Supérieure. I will discuss that in a moment. You can see here the description of this course with a wonderful title, Cours révolutionnaire. How many of you have ever given a revolutionary course? And it's amazing to see that in such a course, he was teaching stereotomy. What is stereotomy? Stereotomy is the art of cutting stones. Once again, engineers, it's a mix of a pure and applied mathematics that I will discuss today. Monge is the best example of a pure applied mathematician who would make no difference between the two aspects of his contribution. So let me put a few dates in order to understand the global situation. Euler, Lagrange, Condorcet, Laplace, Legendre, Fourier, Gauss. I put the dates so that you have an idea more or less of the period of work of Monge. You see, Monge was not so young during the French Revolution. The French Revolution is a matter of young men. And as you see, Monge was not old, of course not. But he was not a young man, but he did a lot of contribution to the French Revolution, including political situation. For example, I will tell you in a moment that he was a minister. He signed the order for cutting the head of the king himself. So he was involved. At the same time, Laplace, Legendre, they went to the countryside to hide. He was in the middle of everything. Okay, so his biography very quickly is this. Until the French Revolution, basically he was a scientist working on everything. Then there was the French Revolution. As I told you, he was very active. And then in 1796, more or less, he fell in love with Napoleon. He was really completely in full admiration for Napoleon. And Napoleon liked him, but he used him a lot. For example, he went to Egypt, and he became a very famous man with beautiful costumes, even more beautiful than my costume. And he became a very important man. And unfortunately, in 1815, when our King Louis XVIII came back after the end of Napoleon, that was a very sad moment for his life, and he died in a very sad way. He was expelled from the Académie des Sciences. So let me tell you a story that in the Académie des Sciences there is statues. And on the left side of the president, there's a statue of Napoleon. And on the right side of the president, there used to be a statue of Monge. But some reason that I don't understand, 2 years ago, somebody had the idea to expel Monge from the Académie des Sciences and to replace him by Lavoisier. So Lavoisier took the place of Monge. Anyway, so let's go to the work of Monge. Once again, you have to keep in mind that Monge was always working on applications, always applications, and trying to see this from the perspective of pure math. So first of all, he started his career in Mézières, in one of the first examples of a school for engineers. Since he was not a noble, he could not be a student there, but he was some kind of assistant. And he worked on several practical problems. Let me tell you. First problem is called in French the défilement. No idea in English. As you see, it's a military question. You have some polygon in the plane, which is supposed to be a castle or a fortification. And around the polygon, you have high mountains. And then you want to build walls to protect you from the enemies. And the question is, how high should be the wall to be protected from the surrounding enemies? This is a very practical question. If the mountains are low, of course, it's not necessary to build a very big wall. So if they are very high, you have to build it very high. And in practice, how should you do? Well, for each side of the polygon, you should imagine a plane rotating around this side and rotating until it touches the summit of the neighboring mountains. So for each side of the polygon, you have a limit plane. And then you have another limit plane, and then another limit plane, and these planes will determine some kind of domain below which you are protected from the enemies. And if you want to protect you from the enemies, you have to build walls in such a way that these planes are above your height. And so the question is, how do you compute these planes just from the map? I give you the map, you have the polygon, you know the height of the mountains, and you have to compute these limiting positions of the planes. This is called the défilement. And Monge found a wonderful method to do that in a much simpler way that was done earlier, and that was useful, as you will see later, in his later mathematics. The second problem is cutting stones. Right? Yes? Yeah. I don't know. Where instead of plane, you have a limiting parabola. Instead of having the envelope of planes, you have, every canon gives. Yeah. Can you see these students criticizing their teacher? Okay, and then you have this wonderful study also trying to understand shadows. You have an object under the light. How do you draw the shadow? This is also a problem that has to be solved geometrically. This is a picture by Monge. And finally, the problem I want to discuss today, the déblai and remblai. Well, I try to find the translation in English. I don't know. In Portuguese, I don't know either. So the problem is this. You want to build something here, and you want to take Earth from here. So this is a hole. This is called the déblai, maybe excavation or something. And you want to transport some quantity of Earth from here to here to build this wall or this castle, whatever. So every particle here from the déblai has to be sent somewhere in the remblai. And what you have to do is to decide which particle goes where. And when you transport this heavy quantity of Earth from here to here, there is a cost. The cost depends on the length of the transportation. And the question that had to be solved is, given the shape of the déblai, given the shape of the remblai, how do you manage to transport the Earth from here to here with a minimum cost? That's the question of déblai and remblai. Okay, let's discuss this problem. Before I do that, I have to explain to you what was known at the time in differential geometry of surfaces. This is a wonderful paper, good time where papers were written in French. Euler was writing this wonderful paper, constructed. Why is it red? No, it's perfect on my computer. Well, okay, it's red. Anyway, so Euler wanted to understand what is the meaning of curvature for a surface. At the time, people knew what was the curvature of a curve in the plane, but they wanted to understand what's the curvature of a surface. And Euler wrote this wonderful paper in which he defines these principal curvatures. That's a very simple idea. You take your surface, take a point on the surface, take the tangent plane, take the perpendicular to the tangent plane, the normal, and intersect your surface with a plane which is rotating around this normal. The intersection of the surface with the plane is a curve, and when the curve is when the plane is rotating, the curvature of the curve is moving from a maximum to a minimum. Maximum and minimum are called principal curvatures. There's a big curvature and a small curvature. This has been discussed by Euler, and these two directions where the curvatures of the intersections are minimal and maximal are perpendicular. This has been understood by Euler. Then I mentioned two papers, one by Euler. You can notice that he was writing in Latin. And at the same time, another paper by Monge on developable surfaces. This is a very natural question. You have a surface in space, and you ask yourself, is it flat? What does that mean to be flat? Can I cover my surface with a sheet of paper with no wrinkles? Can I put a sheet of paper on the surface in such a way that the surface is perfectly adapted to the sheet of paper with no wrinkle? Can I cover my surface with paper? You can see the title. I love this title, even though I don't speak Latin. First of all, it says that it's not discussing surfaces, but solids. How is it possible that when you discuss surfaces, you discuss solids? The explanation that I like is that if you go to primary school, you will see that people mix in general the disk and the circle. People mix the sphere and the ball. Because for us, in many situations, a surface is nothing more than the boundary of a solid. And during a long, long time, including in Euler's time, a surface could not exist unless it is the boundary of a solid. And then you can see that the title says it's discussing solids that can be explained in the plane, surfaces that you can develop on the plane without creating wrinkles. This is a wonderful paper. There's this other paper by Monge sur les propriétés de plusieurs genres de surfaces, particulièrement sur celles des surfaces développables. And then these two people at the same time, without any connection between the two, created the concept of developable surfaces. So here's the definition. A surface is called developable if you can develop it on the plane. Which means that you can locally it is isometric to a plane. And the theorem of Euler and Monge is that a developable surface has to be ruled, has to be made of lines moving depending on one parameter. Ruled surfaces are not necessarily developable, but developable surfaces has to be ruled. And the characterization of developable surfaces among ruled surfaces is given by this condition. Along a straight line, the tangent plane has to be constant. Let me show you a little movie to show that. Okay. So this is an example. If you go to Beaubourg, you can see this sculpture. This artist from the beginning of the 20th century produced a lot of developable surfaces. And you can see this surface is made out of lines. But some ruled surfaces are not, most ruled surfaces are not developable. You can see, for example, the hyperboloid like that is ruled, but it's not developable because you can see that the tangent to the line is moving when you go along the straight line. So this is a ruled surface which is not developable. Okay. Now Monge and Euler proved the following theorem. The following conditions are equivalent. The surface is applicable on a plane. It's a ruled surface whose tangent plane is constant along the lines. It is an envelope of one parameter family of planes. And it is the surface swept by all tangents lines to a space curve. You take a curve in the space. Each point on the curve, you take the tangent. And you look at the surface described by these tangents moving in space. And you get a developable surface. And all developable surfaces are done like that. Here's some pictures. This is a picture for Monge. And this is an example of a developable surfaces. You have an helix. And at each point on the helix, you take the tangent. And these tangents describe this surface that you can see here, which is developable. And to show you that this surface is developable, I show you how to develop it on the plane. You see, just move the curve to the plane, and you can see that the surface is developed on the plane. Okay. Now, here's another example of a developable surface. Yeah. If you take a curve in space, and if you take the tangent to this curve, the corresponding surface will have two sides and will be singular along the curve. They will approach like a cusp. So the surface is approaching like transversally, it's like a cusp. Okay? And this is another example of a developable surface. Take a wire and take the convex hull, and you see that the white part on this picture, or I should say the pink part on this picture is developable because you can develop it on the plane. You can roll it on the table, and it will be developed. It will be applicable. It is applicable on the plane. Okay, so these developable surfaces are in the heart of all the work of Monge. This is another example of the developable surface. You see, you have a family of planes, and they envelope a surface, which is developable. Okay, let's go to this memoir on Deblay and Remblay. I will try to convince you that this is a mix of pure and applied mathematics, and that in practice, he starts with a problem from transporting Earth from Deblay to Remblay. He claims he solves it, which is not true. But for him, it's a good opportunity to do mathematics, pure mathematics. So let me show you. At the end of the paper, it's a long paper, he claims that the solution of this problem is far from being usable in practice. So he's very honest. He builds a long paper, and at the end of the paper he says, well, my solution is not usable. But this gives us some opportunity to publish some new and remarkable properties of curved surfaces. So once again, he is interested by applications, but these applications led him to pure mathematics. He's happy with that, and he's honest enough to mention that. So let's go to the problem. First part, he says, let's forget about three-dimensional things, and let's go to two-dimensional things. So instead of having some three-dimensional object, you have a domain here in the plane, and another domain in the plane. You assume that they have the same area, and you try to transport one to the other. So each point x should be mapped to a point f of x. This map from here to here has to be area preserving. And this map should minimize the integral of the distance between x and f of x over all possible transportation maps. So you try to minimize the transport from one domain to some other domain, and you want to do that at the lowest possible cost. First observation, at no moment Monge has any doubt about the existence of a minimum. For him, it's obvious there should be minimum. So he does not even discuss the existence of minimum, and it's good news because the proof that there is indeed a minimum for such a map has been obtained by Ambrosio some 15 years ago. Then he comes with the first lemma. And the lemma is the roots can only intersect at endpoints. Here's the picture. Suppose you had that. The point A goes to B, to f of A. And suppose B goes here. If this is the route from A to f of A, and this is the route from B to f of B. And Monge says, no, such a situation is not possible. Because if you had such a crossing of the routes, it would be much better to send A here and B here. By triangle inequality, it is much more, it's less costly to go from here to send A to f of B. I mean, this plus this is less than the sum of the two diagonals. So if you take the minimum, well, the roots cannot cross. That's the lemma. And then he says from that, you get the solution. And the solution is this. You have these two domains. With the same area. Say that the area is 1. And choose some number s between 0 and 1. And look at all lines which divide the first domain in area S1 minus S. S1 minus S. You can see that this is a one-parameter family of lines. If you want to cut the first domain in S1 minus S, it's a one-parameter family of lines. And this one-parameter family of lines will intersect the second domain and will not cut in S1 minus S, but if you, by continuity, at some moment, there will be a unique line at some moment there will be a unique line such that on both sides you have S1 minus S, S1 minus S. So for every S between 0 and 1, there is a line going from the first domain to the second domain, dissecting the first in S1 minus S and the second in S1 minus S. So you do that for each S from 0 to 1, and you get a moving line. Here you can see on the picture. So these are the lines which have the property that on each side, each of the two domains are dissected S1 minus S. And you can see the picture here. And Monge says, OK, I'm done. It's enough to take a transportation which maps each interval like that to the corresponding interval here. So that's very practical. You take your two domains, you compute the family of lines which dissect each of the two domains equally on the left and the right. Yes? Exercise for you. Well, it's sending this to this. So it's sending S to S. Okay? So it's area preserving. So it's a homeomorphism, sending the first domain to the second one. And according to Monge, that's the solution. OK, so that's what he explained in the first part of his paper. And at the end of the paper, he mentions that this being said, at the end of the paper, this being said, all the previous discussion can only be true if otherwise the previous solution is illusory. Anyway, he explains why his proof is not correct. It's sometimes correct, but sometimes it is not. And it is not in such a situation. Let me show you. This is a picture not from Monge, but from Dupin, a student of Monge. You should not be afraid by the fact that these curves are not straight lines, because Dupin wanted to transport not according to straight lines, but according to the slope of the terrain. And so he wanted to accept curves which are not straight lines. But you see that the point is that there is no reason to believe that the lines that I mentioned here, there is no reason to believe that they do not intersect. It might happen that we could have such a situation. Oops. And then you don't know how to do, because the point here is on two segments, on this one and this one. And you don't know if you should send it here or here. So in some situations, the solution of Monge is illusory. Nobody knows how to do till today. And I want to mention you as an open problem, a sleeping problem, as Arnold would say. This is, even for simple domains, I don't know the answer. So let me give you one example. I will come back to that at the end. As you may know, Cédric Villani wrote two thick books, 1,000 pages each, on optimal transportation on this topic. And once, I was some kind of, I was checking the book when he was writing it. And when I said to Cédric, here's a disk, here's an ellipse with the same area. How do you do? And he said, Etienne, do not ask questions that are too complicated. So one of the sleeping problems is try to transport one ellipse to another ellipse. What can you do? This is a completely open question. What is the best way to transform an ellipse to another ellipse? Nobody knows. Okay, so that was the dimension 2 case. And then let's go to dimension 3. Now you want to transport some domain in the space to some other domain in the space. First of all, it is not clear to me that this has anything to do with applications. Because if you have Earth and you want to transport Earth, you're not going to use an airplane. Huh? So this is completely ridiculous to try to minimize transportation in the air from one domain to the other domain. Anyway, so this is for Monge, this is an opportunity to discuss three-dimensional problems. So he introduces what's called today a congruence. A congruence is a family of lines depending on two parameters. We had here a family of lines depending on one parameter. Now you have a family of lines depending on two parameters, something like that. On each point on this green, on this yellow square, you have a corresponding line. And then Monge wants to understand the structure of these congruences. Okay, here's the yellow square. Each point on this square is a line. Now, if you take on this square a curve, this gives a family of lines. This gives you a ruled surface. And the question of Monge is, can I choose the line in such a way that the ruled surface is developable? Can I choose a curve in the yellow square in such a way that the corresponding surface is developable? And it proves the following. There are two families of lines, two families of curves, such that along those curves, the corresponding ruled surface is developable. And he proves it. Here's the proof. You see the style. Avant d'entrer en matière, je vais établir quelques propositions de géométrie sur lesquelles sont fondées les recherches. Alors, the proof is this. Take a point x, y, 0 in the yellow square, and you take the line considered by a of xy, b of xy, 1. Then what Monge does is that he looks at the line which corresponds to an infinitesimally closed point, x plus dx, y plus dy, and he wants to know when these two lines are coplanar. The equation is some kind of determinant. Of course, Monge is not using determinant because determinant did not exist at the time. And he discusses that, and he proves that this is second-degree equation in dy dx. So there are two solutions. Well, Monge seems to ignore that some second-degree equations have no real solutions. But he doesn't care. He continues working as if these two solutions were real. And these two solutions give these two directions that you have to follow if you want to have developable surfaces. And the theorem is that he gets is this. This is a complex of lines. In yellow, you have all the lines the same family. This is developable surface. And in blue, you have all the lines in the other family, which defines another developable surface. So what Monge says is that it follows that the lines are nothing but intersections of two families of developable surfaces, such that any surface of the first family intersects each one of the second family along a line. So he proves that, except that he's cheating a little bit because the line may be complex and not real. Anyway, let me show you an example. You have these two, you have the green lines, the yellow lines, defining two developable surfaces, and it has this picture that any complex of lines can be seen as the intersection of two families of developable surfaces. Okay, what can you do with that? He says, okay, nothing. what we can do is that we can connect with earlier paper by Euler and try to understand the situation for curvatures of surfaces. Let me show you. Okay, so this is a piece of a surface with negative curvature. And then from each point of this surface, I will draw the normal. First of all, on one position. And this is a complex of lines. And you can see that in this specific example of complex of lines, you get the definition of principal curvatures from Euler. You see that the normals envelope the normal to a principal curvature line is developable surface. And if you go on the other direction, you have the same picture with the other curvature and the other developable surfaces. Look at that. Now let's look at the other side. You see that these straight lines, they envelope two families of developable surfaces that you can see here, so that you get this famous picture from differential geometry due to Monge, that for every piece of surface in 3 space, if you draw the normals to all points on the surface, you will create such an object which consists of 2 families of developable surfaces. This picture, you should see it as the exact analog of the 2-dimensional picture which is here. And the theorem of Monge is that this should be the roots followed by an optimal transport from one 3-dimensional object to some 3-dimensional object. The only way to transport in a minimal way an object to another object is to follow this kind of lines. This is more or less proved by Monge, but the truth is that he claims that this is obvious. He does not prove it. You had to wait for Dupin to get a reasonable proof. Anyway, so the theorem of Monge is that if you want to transport some 3-dimensional object to some other 3-dimensional object, you should find a surface in between the 2 objects such that the roots are the perpendicular to that surface. Now, if I give you one object and some other object, you look for a surface in the middle whose perpendicular would help transporting one to the other. How should you do that? Well, you should express the fact that this is volume preserving. Now, to express the fact that this is volume preserving, you have to compute the Jacobian of the map. The Jacobian of the map will depend on the normal of the surface. And this gives rise to a differential equation, which is here. And this is a partial differential equation that all experts recognize immediately as the Monge-Ampère equation. The Monge-Ampère equation tells you you want to find a surface whose Jacobian of the normals is given. In practice, you want to find, this is nonlinear partial differential equation, which is nonlinear only through the Hessian. You can see on the top right the Hessian of the unknown function. Now, the end of the paper of Monge is very surprising. This is 1781, so almost nothing was known about partial differential equations. Monge was convinced that a second-order differential equation, partial differential equations, depends on 2 functions. That's not true. So he proposed a solution. Unfortunately, the solution is not correct. But at the end, he says that he knows that this is not correct. And he says that somebody else will improve that later. OK, so let me finish that by mentioning the end of his life. In 1792, as I told you, he became minister of the Comité de Salut Public. Then he began founding the École Centrale des Travaux Publics. then the École Polytechnique, then the École Normale de l'An-3, which is the predecessor for the École Normale Supérieure. He was fully involved in teaching, and then this is the this is the door of the École Normale Supérieure, and then he was teaching a lot in École Polytechnique. He was in love with the École Polytechnique. He gave many, many courses there, including this one on stereotomy. And then, to tell you how much he was important, I told you he fell in love with Napoleon. And Napoleon asked him, would you imagine that? Napoleon asked him to go to Italy and to take all these art, fantastic pieces of art in museums, in churches, and to take them back to the Louvre. So he was in charge of stealing all these things. But since he was a scientist, he realized that the Parmigiano, no, the cheese from Italy is very good. So he wrote a paper on how to use that and to copy the Italian cheese in France. So he was interested by everything. And then Napoleon, to thank him, made him, how do you call that, a comte d'Empire. And unfortunately, the colors are not good. And that's the end of his life. But now I want to tell you another story to finish my talk. This is a sad story. In 1884, the French Academy of Sciences realized that the paper of Monge was very interesting, but nothing was proved. So they decided to establish a competition, a prize, for the mathematician who could improve or at least fix the paper of Monge. And they proposed a 3,000 francs prize. 3,000 francs at the time was 1 year of a salary of a university professor. So he proposed to fix the paper of Monge. We are in 1884. Then there was a competition, and there were several candidates, 3 candidates at least, and the Academy decided to give the prize to Paul Appel. Paul Appel is a very renowned mathematician. I will discuss that in a moment. And the guy who lost the competition is called Monsieur de Saint-Germain. So here's the memoir of Appel, Mémoire sur les déblais et remblais, 1884, by Monsieur Appel, the winner of the competition. And this is the memoir, of Saint-Germain, who lost the competition. You find this first memoir of Appel in the publication of the Académie des Sciences, and you find this one in the Académie des Sciences de Caen. Okay, 1884. Now let's go to 1928. Much, much later. 1928, Mr. Appel, who was recteur honoraire de l'Université de Paris, a powerful man, published a paper with the same title. You see, le problème géométrique des déblais et remblais. It turns out that when I was trying to understand the history of these papers, I had photocopies of all these memoirs. I was in a bus in Chile, and I had on my I had the 2 photocopies of, by chance, the photocopy of the memoir of Appel 1928 and the memoir of Saint-Germain, who lost in 1884. And I realized that Appel copied word by word, the full paper of his competitor. So I was very surprised by that. And I wrote this in a footnote somewhere. And I received a message from a Brazilian historian who told me this is not possible. I mean, Appel is such a great man. Appel, you can see him. You know, he is a great man. Huh? Appel many people say that he's somehow the founder of CNRS. He was defending Dreyfus. He was for the peace, and he was a very important man with no criticism. How is it possible that such a powerful man could copy the work of some colleague 40 years earlier in a competition that he won? So I sent the proof of what I said to this historian mathematician, and he answered, yes, you're right. How is it possible? And he decided, with a colleague from Dijon, to study this case. How is it possible? What happened? What is the concept of plagia? I mean, when mathematicians understood, you know, what I was told that, for example, in music, copying, I mean, Bach copying some other musicians is not a shame. But in mathematics, we are very proud of that. I mean, you cannot copy the work of somebody else, even 40 years earlier. And they published a paper, which is very interesting, that I recommend, thinking about what is property in mathematics. The strange case of Paul Appel's last memoir, Monge problem. And there are many possible explanations. One of them is that at the time, even great professors like Paul Appel, well, maybe they need money. He was an old man. There was no retirement. Another possible situation is that, would you believe it, according to them, maybe his wife wrote the paper to make money. Another possibility is that at the time, editors needed papers to publish. And one of the possibilities at the time, it was good old times where papers by professors were written by students. And it is possible that Paul Appel didn't even see this paper, which was written by some of his students. Anyway, I think it's a very interesting situation, trying to understand what is the meaning of plagia. When we use the theorem of somebody else, of course, if you use word by word, it's too much. But sometimes it's unclear to us. Huh? Anyway, finally, to finish my talk, let me say something that when Monge wrote his paper, the fact that there is a minimum for this minimization procedure for him was obvious, no question about that. We forgave him. In 1884, when Appel and Saint-Germain had the same problem and did not discuss the existence of a minimum, I don't forgive them. Because at the time, we had already the same problem for the Dirichlet problem. Minimizing energy, is it possible? Is there a minimum? So people were aware of that. And I'm sure that Appel and Saint-Germain were aware of that. But in 1918, publishing a paper without questioning the existence of minimum is simply a shame. So shame on Appel. Thank you.